Everyone, this is pre-class video on module 4 unsymmetrical fault analysis. In this video I will be explaining problems on the unsymmetrical faults. Myself Dr. M.J. Chandrasekhar, Associate Professor, Department of EEE, SJB Institute of Technology. So in the previous 3 sessions I explained the theoretical aspects of unsymmetrical faults. So introduction to unsymmetrical faults, the LG fault, LL and double line to ground fault, open conductor fault, all these different types of faults, finding the fault current and the sequence network we have studied. In this session I am explaining the solving numericals on finding the short circuit current under unsymmetrical faults. See here we have considered the first example. So first I will read the question. The line currents in a 3-phase 4-wire system are IA, IB, IC. The complex values are given. It is asked us to find the symmetrical component of neutral current. So here we have the formula for finding the symmetrical components. So we can use this formula IA0, IA1, IA2. So that is given by 1/3 of 1 A square 1 A square A and IA, IB and IC. With this matrix equation you can write the symmetrical component of currents, that is IA0. IA0 is 1/3 of IA plus IB plus IC. Similarly you can write IA2 is 1/3 of IA plus A square times of IB plus A square times of IC, and IA1 is given by 1/3 of IA plus A square IB plus A times of IC. So this can be written as, here IA, IB, IC values are given. Substitute these values, use calculator in complex mode to find the symmetrical component of currents. And the neutral current is 1/3 of IA plus IB plus IC, because it is star connected, neutral is grounded. Therefore this is the neutral current formula. By knowing the IA, IB, IC, and you can find the neutral current. So here in this problem it is also asked us to find the symmetrical component of currents. So one can find the symmetrical component of current in terms of phase A as IA0, IA1, IA2 as I explained. Similarly, one can find in terms of B phase IB0, IB1 and IB2, and similarly for C phase symmetrical components are IC0, IC1 and IC2. As you know that the zero sequence components will have the same magnitude, and the angular displacement is 0. Therefore IA0 will be equal to IA1 and IA0 is equal to IB0 and IB0 is equal to IC0. But positive sequence, this is zero sequence. For positive sequence, as we know, here it has 3 phases, they are all equal in magnitude and they are phase spread by 120 degree. They are phase spread by 120 degree. This is IA1, IB1, IC1, this is A, this is A square. So A is 1 at an angle of 120, A square is 1 at an angle of 240 and A cube is 1. So IB0 and IC0 I told you how to find. IB1, here I can find IB1. IB1 is A square times of IA1, and similarly IB2 is A times of IC1 is A times of IA1. Here from this diagram you can find the IB1 and IC1 in terms of this. I explained in the symmetrical components in the beginning session. So, use this because already we found IA0, IA1, IA2. By knowing this, you can find the remaining 6 parameters as per this procedure. Similarly, the negative sequence network, this is positive sequence network values, and negative sequence components are the same lines. It has 3 phasors, they are all equal in magnitude, VA2, VB2 and VC2. This is reference, this is A and this is A square. So, here also you can write VB2 as A square times of VA2 and VC2 is A times of VA2. By knowing this VA2, can find VA2 here nothing but current, right, current. So, by knowing IA2, you can find IB2 and IC2. So, this is how one can find the answer for symmetrical components. Second problem, here it is required to find the sequence component of voltages of phase voltage of a 3-phase system. Here also VA0, VA1, VA2 is given. It can be solved. VA0, VA1, VA2 is given. It is required to find the values of, determine the phase voltages VA. VA, VB, VC phase voltages, this can be written as 1, 1, 1, 1, 1 A square A, 1 A square into VA0, VA1, VA2. See here VA0, VA1, VA2 are given. So, A is 1 at an angle of 120 and A square is 1 at an angle of 240. By knowing this, you can find the values of phase voltages VA, VB, VC. After this, we will take up the next problem. Here, the 2 sequence components and the corresponding phase voltages of a 3-phase system are given. So, that means here VA1 and VA2 are given and VA is given, determine the other phase voltages. So, here VA is given, VB and VC is required to find, VC and VB it is required to find. It is a 3-phase system. For a 3-phase system, so here VA, VB, VC, 2 symmetrical sequence components and the corresponding phase voltages are given. So, VA can be written as 1/3 of VA can be written as VA0 plus VA1 plus VA2. Here VA is given, VA0 is given, VA1 is given, you can find VA2. So, after finding that, you can find VB. VB is VA0 plus A square VA1 plus A times of VA2 can find. Similarly, VC can be VA0 plus A times of VA1 plus A square times of VA2. So, using these formulas, you can find the values of VA, VB, VC. That means the phase voltages VB and VC you can find. So, next we will see the next problem. So, here Z0, Z1, Z2 are given, compute the fault current and Z0 is given, Z1 is given, Z2 is given, compute the fault current and voltages line to line fault. Note that the sequence impedances are in per unit, this means that the solution of the current and voltage will be in per unit. So that means sequence network, positive sequence network, negative sequence network, it has only two sequence networks, Z1, Z2, and this is EA. They are connected in parallel. So Z1 is given, Z2 is given, and Z0, because it is a line to line fault, Z0 value will be 0. So then we have to compute the fault current. Fault current is given minus J root 3 into EA divided by Z1 plus Z2. Here voltages are not given, you consider that as 1 at an angle of 0, ideal condition. Z1 and Z2 are given. By using this you can find the fault current. And voltages for line to line fault, voltages VB and VC. VB you see here, you can find VA1 and here VA2. By knowing VA1 is EA minus IA1 into Z1, this is IA1 and this is IA2. By knowing the sequence currents and sequence impedances, you can find the sequence voltage. Next we will consider one more example. So here it is required to find the x1, x2, x0. It is required to find the values of x1, x2, x0. The question here is, it is a 3-phase 500 MVA 11 kV star connected generator is subjected to a different types of faults while operating at rated voltage and on no load. The sustained faults are, the sustained fault 3-phase fault is given and line to line fault is given and single line to ground fault is given. We have to find the reactances both in per unit and in ohms, and also find the double line to ground fault at the generator. So this is very simple. First we have to consider the 3-phase fault. So 3-phase fault here we have to consider. After finding the 3-phase fault, the value of IA1 here is EA divided by Z1. So here Z1 is nothing but EA divided by IA1. Here the fault current IA is IA0 plus IA1 plus IA2. Okay, here 0, negative and 0 sequence, negative and 0 sequence won't be there. You will be having only the positive sequence. Therefore, IA1 will be your fault current. So Z1 is your x1, that is EA is 1 divided by 11 is 1. So per unit we have to consider. Then this is the fault current. Fault current value 2000 is given. So if you consider this as 11 kV into 10 to the power of 3, the answer here is will get 3.17 ohms. 3.17 ohms. Similarly, you can consider the line to line fault. So in the line to line fault, we have the expression IA1 is EA divided by Z1 plus Z2. So here it is minus IA2. From the line to line fault derivation, we know that this is IA0 is 0, we know, and the fault current expression we know, minus J root 3 EA divided by Z1 plus Z2. Here the line to line fault current is 1800 amps is given. This is 11 kV into 10 to the power of 3. Z1 is 3.17 is given. So the only one is Z2. So with this you can find Z2 resistances. If you neglect, that is x2, that value you will get it as 6.11 ohms. 6.11 sorry, here if you simplify further, you will get this value as x2 as 2.94 ohms. So next we will consider the one more fault, that is double line to ground fault. Double line to ground fault we will consider. So if you consider the double line to ground fault, line to ground fault, here line to ground fault is of 3 times of EA divided by Z1 plus Z2 plus Z0 is the formula. Here Z1 is known, Z2 is known, Z0 is not known. The fault current here it's given it as 2200. So if you, this is the phase voltage, we know that is 11 kV phase value divided by root 3, that is line to line value. So if you simplify this, you will get Z0. If you neglect the resistance, it will be X0, and 1.06 per unit you will get. So this is how we can find the reactances in per unit as well as reactances in ohms per unit. Actual value means if you want, then you have to find the ZB, that is VB square by SB. Here the voltage is 11 square divided by SB value is 50. This should be in kilovolts and this should be in MVA. So if you consider this, you will get this as 24 ohms. So if you want actual value of X0, so per unit value multiplied by base value, that is 1.06 multiplied by base value. Base value is 24. Then X0 you will get. So please calculate and come to know that this value is around 24 ohms. With this, I will be ending this video.